Hall thrusters are a widely used type of spacecraft propulsion device. Instead of combusting a chemical fuel like a typical rocket, Hall thrusters employ electricity to ionize a propellant, which can then be accelerated by an electric field to produce thrust. This produces much less thrust than a chemical rocket, but is far more efficient, enabling missions which carry more payload for a fixed launch mass, and which in some cases can even be faster than those launched by a chemical rocket. Let's take a look at how one of these devices works. Hall thrusters have only a few key parts. There is a discharge channel, typically made of a ceramic, a metallic anode, and a hollow cathode. To start the thruster, we apply a voltage between the anode and the cathode. This sets up an electric field, which causes electrons emitted from the cathode to migrate toward the anode, completing the circuit. Electromagnets embedded in the thruster produce a magnetic field perpendicular to the electric field. Since electrons orbit magnetic field lines, this field acts to halt the electrons on their path from cathode to anode. The combination of crossed electric and magnetic fields also induces the electrons to rapidly circuit the thruster at speeds approaching and even exceeding 1,000,000 miles per hour. This so-called Hall current gives the thruster its name. At the same time, a neutral gas, typically xenon or krypton, is injected at the anode and begins to diffuse downstream. Every so often, a drifting electron impacts a neutral atom. Sometimes these collisions have enough energy to knock an electron off of the neutral atom. This produces a positively charged ion and a second electron, which joins the Hall current. The more electrons there are, the greater the probability of collisions, and in this way, more and more ions are produced in a process known as avalanche ionization. The resulting fluid of ions and electrons is known as a plasma. The positively charged ions in the plasma feel the applied electric field and are accelerated downstream at tens of thousands of miles per hour, producing a small amount of thrust. Enough electrons follow them such that the device remains electrically neutral overall. Every time an electron collides with a neutral or an ion, it loses a small amount of momentum and drifts a bit closer to the anode. In this way, the electrons are able to complete their path from cathode to anode despite the presence of the magnetic field. However, the electron current that actually reaches the anode is much higher than what we would predict even when accounting for all types of collisions. The cause of this enhanced, so-called anomalous transport is unknown and is an active area of research. However, as a result, we cannot simulate these devices in a way that predicts their thrust, efficiency, and other key performance metrics from their geometry and operating conditions alone. My research at the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory focuses on improving our ability to model anomalous electron transport in order to build predictive simulations of Hall thrusters. Many research groups attempt to capture this critical phenomenon via high-fidelity, three-dimensional particle-in-cell simulations. However, such simulations take months to complete on thousands of CPU cores, making them highly impractical for most engineering design purposes. Instead, I am focused on developing simpler models of the anomalous electron mobility that can be implemented into fluid simulations which may run in a matter of hours. Without predictive models, developing a new Hall thruster must instead rely on lengthy and expensive ground tests in a vacuum chamber. With better models, we can more accurately predict how a Hall thruster will operate in space, opening the way for more rapid simulation-based design optimization and reducing the cost of prototyping, testing, and qualifying these devices. This will in turn pave the way for developing new generations of Hall thrusters, which can operate at both very low and very high power levels, employ exotic propellant gases, and even use unconventional magnetic field shapes and geometries. With such improvements, these thrusters might be used to take humans to Mars and beyond.